Hello, yeah, okay, sorry. Hello and welcome back to the Learn Along series. We are currently studying NLP with deep learning. This is a course from Stanford. Uh, I believe this is stream number 23. Uh, for today, we'll be uh, sitting through the lecture number 14 on transformers and self-attention. I believe the professor had invited uh, the original author of the Attention is All You Need paper. Uh, I think I'm forgetting the name of the individual, but he was in the Google Brain team. Not sure if he still is or at the time he was, but because I think the paper came out in 2017. But let's see, I'm actually super excited because quote unquote this is still more or less the state of the art. I mean, there are obviously newer uh, methodologies and papers that have come out, um, but let's get on with today's lecture. Quickly switch. Here we go. Lecture 14, Transformers and Self-attention. Here we go.
Okay, so I'm delighted to introduce our first lot of invited speakers, and so we're going to have two invited speakers today. So starting off, we're going to have Ashish Vaswani, who's going to be talking about self-attention for generative models, and in particular, we'll introduce some of the work on transformers that he is well known for, along with his colleagues. And then as a sort of a special edition, we're then also going to have Anna Huang talking about some applications of this work. There are actually at least a couple of people in the class who are actually interested in music applications. So this will be your one chance in the course to see music applications of deep learning. Okay, so I'll hand it over to Ashish.
Thanks, Chris, and thanks, Abby. Anna's actually here to make the class less dull, so she's the highlight, not this guy. So, hi, everyone. Excited to be here. This is a very large class. First invited speaker, no pressure, so hopefully this will all go well. So the talk is going to be about self-attention. And so the purpose is not going to be just to talk about a particular model, but as empiricists and like, well, I'm an empiricist and I consume machine learning to apply it to various tasks, and a starting point always is to ask this question, you know, what's the structure in my data set, or what are the symmetries in my data set, and is there a model that exists that's a very good, that has the inductive biases to model these properties that exist in my data set. So hopefully over the course of this lecture, Anna and I will convince you that self-attention indeed has the ability to model some inductive biases that potentially could be useful for the problems that you care about. This talk is going to be on learning representations, primarily of variable length data. Well, we have images, but most of it is going to be variable length data, and all of us care about this problem because, well, in deep learning is all about representation learning, and building the right tools for learning representations is an important factor in achieving empirical success. Now, the models of choice, the primary workhorse for perhaps even now or up to this point, have been recurrent neural networks. How many people here are familiar with RNNs? Okay, so definitely up to this point, the primary workhorse have been recurrent neural networks, and some of the more some gated variants that explicitly add multiplicative interactions like LSTMs. They also have mechanisms that allow for better gradient transfer, and some recent variants like gated recurrent units that are simplification. They're kind of they dominate this recurrent landscape. And typically, how do recurrent neural networks learn or produce representations? They consume a string or a sentence, even an image. Imagine, you know, sequentially, and at each position, at each time step, they produce a continuous representation that's a summarization of everything that they've actually crunched through. Now, so in the realm of large data, having parallel models is quite beneficial. In fact, I was actually reading Oliver Selfridge. He was a professor at MIT, and he had this he wrote the precursor to deep nets. It's called Pandemoniums. I would recommend everybody to read it. And he has this fascinating note that, if you give me more parallel computation, I'll just add more data and make it slower. So you can consume more data. And recurrence sort of just by construction limits parallelization, because you have to wait for a particular time point to produce the representation. By the way, if there's any questions, please raise your hands. I'll hopefully look around and be able to attend to your question. And again, and now because we're actually producing these representations, we're sort of summarizing, if you want to pass information, if you want to pass co-reference information, then we kind of have to shove all of this inside this fixed size vector, so it could potentially be difficult to model. And while they've been successful in language, the architecture doesn't have a very clear, explicit way to model hierarchy, which is something that's very important in language. So there's been excellent work, precursor to self-attention, that actually surmounted some of these difficulties. So what were these difficulties? Basically, it's like convolutional sequence models, where you have these limited receptive field convolutions that again consume the sentence, now not sequentially but in depth. And they produce representations of your variable length sequences. They're trivial to parallelize because you can apply these convolutions simultaneously at every position. Each layer is trivial to parallelize. The serial dependencies are only in the number of layers. You can get these local dependencies efficiently because a single application of a convolution can consume all the information inside its local receptive field. Now, if you want to have these really long distance interactions, while you don't have to pass through linear number of steps, you still, because these receptive fields are local, you might need something like linear in depth, or logarithmic if you're doing something like dilated convolutions. So they still need, the number of layers that are needed are still a function of the length of your string. But they were a great development, and they actually pushed a lot of research, like wave RNN, for example, is a classic sort of success story of convolutional sequence models, even ByteNet. Now, so far, attention has been like one of the most important components, the sort of content-based, memory retrieval mechanism. And it's content-based because you have your decoder that attends to all this content. That's your encoder, and then just sort of decides what information to absorb based on how similar this content is to every position in the memory. So this has been a very critical mechanism in neural machine translation. So now the question that we asked was, like, why not just use attention for representations? And now, here's what sort of a rough framework of this representation mechanism would look like. The way of just sort of repeating what attention is essentially. Now imagine you want to re-represent the word represent. You want to construct its new representation, and then first you attend, or you compare yourself. You compare your content, and at the beginning it could just be a word embedding. You compare your content with all your words, with all the embeddings, and based on these compatibilities or these comparisons, you produce a weighted combination of your entire neighborhood, and based on that weighted combination, you summarize all that information. So it's like you're re-expressing yourself in terms of a weighted combination of your entire neighborhood. That's what attention does, and you can add feed-forward layers to basically sort of compute new features for you. So the first part is going to be about how, like, some of the properties of self-attention actually help us in text generation, like what inductive biases are actually useful, and we empirically show that indeed they move the needle in text generation. And this is going to be about machine translation, but there are other work also that we'll talk about later. So now with this attention mechanism, we get a constant path length. So a position can interact with any position, every position simultaneously. Hopefully, if the number of positions is not too many. Attention, just by virtue of, like, it's a construction, you have a softmax, you get these gating and multiplicative interactions. And again, I'm not going to be able to explain why, but it's interesting. Like, you've seen these models, like even Pixel CNN, when it was actually modeling images, they explicitly had to add these multiplicative interactions inside the model to to basically beat RNNs. And attention just by construction gets this because you're multiplying the attention probabilities with your activations. It's trivial to parallelize. Why? Because you can just do attention with matmuls, especially the variant that we use in our paper, in our work. And so now the question is, convolutional sequence models have been very successful in generative tasks. For text, can we actually do the same or achieve the same with attention as our primary workhorse for representation learning? So just to sort of add some context, and there's been some up to the transformer, there'd been a lot of great work on using self-attention primarily for classification within. There was work on self-attention within the confines of like recurrent neural networks. Perhaps the closest to us is memory networks by West and Zuckbutter, where they actually had a version of recurrent attention, but they didn't actually. Empirically, they didn't show it to work on sort of conditional modeling like the translation, and their mechanism was like they were using sort of a fixed query at every step. So it leaves something to be desired. They still had this question: is it actually going to work on large-scale machine translation systems or large-scale text generation systems? So this is sort of the culmination of the self-attention, our self-attention work. This is and we put it together in the transformer model. And so how does this look like? So we're going to use attention primarily for computing representations. So if your input, imagine you're doing English to German translation, so you have your words. And notice that attention is permutation invariant, so you just change the order of your positions. You change the order of your words, and it's not going to affect the actual output. So in order to maintain order, we add position representations. And there's two kinds that we tried in the paper. These fantastic sinusoids with Noam Shazir invented, and we also use learned representations, which are very plain vanilla. Both of them work equally well. So first we have, so the encoder looks as follows, right? So we have a self-attention layer that just recomputes the representation for every position simultaneously using attention. Then we have a feed-forward layer, and we also have residual connections, and I'll sort of give you a glimpse of what these residual connections might be bringing. That is, between every layer and the input, we have a skip connection that just adds the activations. And then this tuple of self-attention and feed-forward layer just essentially repeats. Now on the decoder side, we have a sort of standard encoder-decoder architecture. On the decoder side, we mimic a language model using self-attention, and the way to mimic a language model using self-attention is to impose causality by just masking out the positions that you can look at. So basically, the first position, it can't look forward. It's illegal to look forward. It can look at itself because we actually shift the input. So it's not copying. It's kind of surprising with these models. It's very easy to copy. At one point, when early on, it was even hard to do copying with recurrent models. But now at least we can copy really well, which is a positive sign, I think, overall. So now on the decoder side, we have this causal self-attention layer followed by encoder-decoder attention, where we actually attend to the last layer of the encoder and a feed-forward layer, and this triple repeats a few times, and at the end we have the standard cross-entropy loss. So sort of staring at the particular variant of the attention mechanism that we use, we went for simplicity and speed. So how do you actually compute attention? So imagine you want to re-represent the position E2, and we're going to first linearly transform it into a query, and then we're going to linearly transform every position in your neighborhood, or let's say every position at the input, because this is the encoder side, to a key. And these linear transformations can actually be thought as features, and I'll talk more about it later on. So it's basically a bilinear form. You're projecting these vectors into a space where just a dot product is a good proxy for similarity. Okay, so now you have your logits. You just do a softmax compute a convex combination, and now based on this convex combination, you're going to then re-express E2, or in terms of this convex combination of all the vectors of all these positions. And before doing the convex combination, we again do a linear transformation to produce values. And then we do a second linear transformation just to mix this information and pass it through a feed-forward layer. And this is And all of this can be expressed basically in two matrix multiplications. And the square root factor is just to make sure that these dot products don't blow up. It's just a scaling factor. And why is this mechanism attractive? Well, it's just really fast. You can do this very quickly on a GPU, and you can do it simultaneously for all positions with just 2 matmulls and a softmax. On the decoder side, it's exactly the same, except we impose causality by just adding 10e minus 10e9 to the logits. So it's just, you just get 0 probabilities on those positions. So we just impose causality by adding these highly negative values on the attention logits. Is everything? I thought that was a question. So okay, so attention is really attention is cheap. So because this variant of attention just involves two matrix multiplications, it's quadratic in the length of your sequence. And now, what's the computational profile of RNNs or convolutions? They're quadratic in the dimension, because basically you can just think of a convolution just flattening your input and just applying a linear transformation on top of it, right? So, and when does this actually become very attractive? This becomes very, very attractive when your dimension is much larger than your length, which is the case for machine translation. Now we will talk about cases when this is not true. Then we have to make other model developments. But for short sequences or sequences where your dimension dominates length, attention has a very favorable computational profile. And as you can see, it's about 4 times faster than an RNN. And faster than a convolutional model where you have a kernel of like filter width 3. So there's still one problem. Now, here's something. So in language, typically we want to know like who did what to whom, right? So now imagine you applied a convolutional filter. Because you actually have different linear transformations based on relative distances, like this linear transformation on the word who, on the concept, can learn this concept of who and pick out different information from this embedding of the word I. And this linear transformation, the red linear transformation can pick out different information from kicked, and the blue linear transformation can pick out different information from ball. Now, when you have a single attention layer, this is difficult because it's just a convex combination and you have the same linear transformation everywhere. All that's available to you is just mixing proportions. So you can't pick out different pieces of information from different places. Well, what if we had one attention layer for who? So you can think of an attention layer as something like a feature detector almost, like because a particular, because it carries with it a linear transformation, so it's projecting them in a space which starts caring maybe about syntax, or it's projecting in a space which starts caring about who or what. Then we can have another attention layer or attention head for what, did what, and another attention head for whom, to whom. And all of this can actually be done in parallel, and that's exactly what we do. And for efficiency, instead of actually having these dimensions operate in a large space, we just reduce the dimensionality of all these heads, and we operate these attention layers in parallel, sort of bridging the gap. Now here's here's a little quiz. I mean, is there a combination of heads? Or is there a configuration in which you can actually exactly simulate a convolution, probably with more parameters? I think there should be a simple way to show that if you had more heads, or heads were a function of positions, you could probably just simulate a convolution, but although with a lot of parameters. So it can, in the limit, it can actually simulate a convolution. And also, we can continue to enjoy the benefits of parallelism. But we did increase the number of softmaxes because each head then carries with it a softmax. But the amount of flops didn't change because instead of actually having these heads operate in very large dimensions, they're operating in very small dimensions. When we applied this on machine translation, we were able to dramatically outperform previous results on English, German, and English, French translation. So we had a pretty standard setup: 32,000 word vocabularies, word piece encodings. WMT 2014 was our test set. 2013 was the dev set, and some of these results were much stronger than even previous ensemble models. And on English French also, we had some very favorable results, and we achieved state of the art. Now, stepping back a bit, I'm not claiming that we arrived at an architecture that has better expressivity than an LSTM. I mean, there's theorems that say that LSTMs can model any function. Perhaps all we did was just build an architecture that was good for SGD. Because stochastic gradient descent could just train this architecture really well, because the gradient dynamics in attention are very simple. Attention is just a linear combination, and I think that's actually favorable. But hopefully, as we go on, I'd also like to point out that we do explicitly model all path connection, all pairwise connections, and it has this advantage of modeling very clear relationships directly between any two words. And hopefully we'll be able to also show that there are other inductive biases, that it's not just like building architectures that are good inductive biases for SGD. So frameworks, a lot of our work was initially pushed out in tensor to tensor. Maybe that might change in the future with the arrival of JAX. There's a framework also from Amazon called Sockeye. There's also FairSeq, the convolutional sequence-to-sequence toolkit from Facebook. I'm actually not sure if it has a transform implementation, but they have some really good sequence-to-sequence models as well. Okay, so the importance of residuals. So we have these residual connections between. So we have these residual connections that go from here to here to here, here to here, like between every pair of layers. And it's interesting. So what we do is we just add the position informations at the input to the model, and we don't inject position information at every layer. So when we severed these residual connections and we stared at these attention distributions, which is the center, sort of the middle map is this attention distribution. You actually, basically, it's been unable to pick this diagonal. It should have a very strong diagonal focus. And so what has happened was these residuals were carrying this position information to every layer. And because these subsequent layers had no notion of position, they were finding it hard to actually attend. This is the encoder-decoder attention, which typically ends up being diagonal. Now, so then we said, okay, so then we actually continued to sever the residuals, but we added position information back in at every layer. We injected position information back in, and we didn't recover the accuracy, but we did get some of this sort of diagonal focus back in. So the residuals are doing more, but they're definitely moving this position information to the model. They're pumping this position information through the model. Okay, so now we saw that being able to sort of model both long and short-term relationships, long and short distance relationships with attention is beneficial for text generation. What kind of inductive biases actually appear, or what kind of phenomena appear in images? And something that we constantly see in images and music is this notion of repeating structure that's very similar to each other. You have these motifs that repeat in different scales. So, for example, there's another artificial but beautiful example of self-similarity where you have this Van Gogh painting where this texture or these little objects just repeat. These different pieces of the image are very similar to each other, but they might have different scales. Again, in music, here's a motif that repeats. It could have like various like spans of time between it. We attempted after this to see, well, to ask this question, can self-attention help us in modeling other objects like images? So the path we took was sort of standard autoregressive image modeling, the probabilistic image modeling, not GANs, because it was, well, one, it was very easy. We had a language model almost, so this is just like language modeling on images. And also training with maximum likelihood allows you to sort of measure how well you're doing on your held out set. And it also gives you diversity, so hopefully you're covering all possible different kinds of images. And to this point, we had an advantage that there'd been good work on using recurrent models like PixelRN and PixelCNN that were actually getting some very good compression rates. Again, here, originally the argument was that, well, in images, because you want symmetry, because you want, like, if you have a face, you want one ear to sort of match with the other. If you had a large receptive field, which you could potentially get with attention at a lower computational cost, then it should then it should be quite beneficial for images, and you wouldn't need many layers like you do in convolutions to actually get dependencies between these far away pixels. So it seemed like self-attention was already a good computational mechanism, right? But it was actually interesting to see how it even naturally modeled self-similarity. And people have used self-similarity in image generation. Like, this is this really cool work by Efros where they actually see, okay, in the training set, what are those patches that are really similar to me? And based on the patches that are really similar to me, I'm going to fill up the information. So it's like actually doing image generation. There's this really classic work called non-local means, where they do image denoising, where they want to denoise this patch P, and they say, I'm going to, based on my similarity between all other patches in my image, I'm going to compute some function of content-based similarity, and based on the similarity, I'm going to pool information. So, and exploiting this fact that images are very self-similar. And this has also been sort of applied in some recent work. Now, if you just took this encoder self-attention mechanism and just replaced these word embeddings with patches, and that's kind of exactly what it's doing. It's computing this notion of content-based similarity between these elements, and then based on this content-based similarity, it constructs a convex combination that essentially brings these things together. So it was very pleasant to see that, well, this is a differentiable way of doing non-local means, and we took the transformer architecture and replaced words with pixels. There were some architecture adjustments to do, and so this was basically it was very similar to the original work. And here the position representations, instead of being one-dimensional, because we were not dealing with sequences, we had two-dimensional position representations. Okay, so I pointed out before, attention is a very favorable computational profile if your dimension dominates length, which is absolutely untrue for images, because even for 32 by 32 images, when you flatten them you get 3072 positions. So it's your standard CFAR image. So a simple solution, because convolutions have basically looked at local windows and you get translational equivariance. We said, okay, let's adopt the same strategy. And also, there's a lot of spatial locality in images. But now we will still have a better computational profile if your receptive field is still smaller than your dimension. You can actually still do much more long distance computation than a standard convolution because you're quadratic in length. So as long as we didn't increase our length beyond the dimension, we still had a favorable computational profile. And so the way we did it was we essentially had two kinds of rasterizations. So we had a one-dimensional rasterization where we had a sort of single query block, which was then attending into a larger memory block in this rasterized fashion along the rows. Then we tried another form of rasterization following standard two-dimensional locality, where we actually produced the image in blocks, and within each block we had a rasterization scheme. Again, this image transformer layer was very similar. We had two-dimensional position representations along with
Okay, we have Saurav Maheshwari in the chat. He says, this is a super cool topic, by the way, using attention for images. Okay. By the way, the guest lecturer is basically the author of Attention is All You Need paper. FYI.
With a very similar attention mechanism. And we tried both super resolution and unconditional and conditional image generation. This was Nikki, Parmar, I, and a few other authors from Brain, and we presented at ICML, and we were able to achieve better perplexity than existing models. So Pixel Snail is actually another model that mixed both convolutions and self-attention, and they outperformed us on bits per dimension. So we were measuring perplexity because these are probabilistic models. It's like basically a language model of images, and the factorization of your language model just depends on how you rasterize. In the 1D rasterization, we went first rows and then columns. In the 2D rasterization, we went blockwise, and inside each block we rasterized. On ImageNet, we achieved better perplexities, and so yeah, I mean, we're not at GAN level, right? I mean, this is I think autoregressive image generation by this point had not reached scans. At iClear 2019, there's a paper by Nal that actually uses self-attention and gets very, very good quality images. But what we observed was we were getting structured objects fairly well. Like, can people recognize what the second row is? I said almost everyone said cars. I'm not going to ask who said something else, but yes, they're cars. Yeah, and the last row is another vehicles. So essentially, when structured objects were easy to capture, like frogs and sort of objects that were camouflaged just turned into this mush. But on super resolution, now super resolution is interesting because there's a lot of conditioning information, right? And when you have a lot of conditioning information, the sort of possible, you actually lock quite a few of the modes. So there's only a few options you can have at the output. And our super resolution results were much better. We were able to get better facial orientation and structure than previous work. And these are samples at different temperatures. And when we quantified this with actual human evaluators, we flashed an image and said, "Is this real? Is this false?" And we were able to fool humans like 4 times better than previous results on super resolution. Again, these results are like I guess the latest GAN result from NVIDIA makes this look like a joke, but I mean we're starting later than GAN, so hopefully we'll catch up. But the point here is that this is an interesting inductive bias for images, a very natural inductive bias for images, and there is hope to applying it in classification and other such tasks also. So one interesting thing, just to sort of, both out of curiosity and asking how good is maximum, does maximum likelihood, well, one, does the model actually capture some interesting structure in the world? Second, do you get diversity? Well, maximum likelihood should get diversity by virtue of what it does. So then we did image completion, and why image completion? Because as soon as you lock down half the image to the gold truth, you're actually shaving off a lot of the possible modes, so you have a much easier time sampling. So the first is what we supplied to the model. The right row, the rightmost column is gold, and we were able to generate different samples. But what was really interesting is the third row. So the rightmost column is gold.
Yeah, I mean, if there's something super important, I usually just hide my face. But yeah, I didn't think that was that important.
Now, if you look at the third row, this horse, so actually there's this sort of glimpse or a suggestion of a pole, but the model hallucinated a human in some of these images, which is interesting. Like it does capture, or at least the data teaches it to capture some structure about the world. The dog is just cute, and I guess it also shows that, there was this entire object, this chair, that the model just completely refused to imagine. So there's a lot of difficulty. And I guess Anna's going to talk about another way to exploit self-similarity.
Thank you. So thank you, Ashish, for the introduction. So there's a lot of self-similarity in images. There's also a lot of self-similarity in music. So we can imagine Transformer being a good model for it. We're going to show how we can add more to the self-attention to think more about kind of relational information and how that could help music generation. So first, I want to clarify what is the raw representation that we're working with right now. So analogous to language, you can think about there's text and somebody is reading out a text, so they add their kind of own intonations to it, and then you have sound waves coming out, that's speech. So for music, there's a very, very similar kind of a line of generation where you say the composer has an idea, writes down the score, and then a performer performs it, and then you get sound. So what we're going to focus on today is mostly, you can think of the score, but it's actually a performance in that it's a symbolic representation where MIDI pianos were used and professional amateur musicians were performing on the pianos, so we have the recorded information of their playing. So in particular, at each time step, modeling music as this sequential process, what is being output are, okay, turn this note on, advance the clock by this much, and then turn this note off. And also there's dynamics information. So when you turn the note on, you first say like how loud it's going to be. So traditionally, modeling music as kind of a language, we've been using recurrent neural networks. And because, as Ashish introduced and talked about, there's a lot of compression that needs to happen. Like a long sequence has to be embedded into like a fixed length vector, and that becomes hard when in music you have repetition coming at a distance. So I'm first going to show you samples from the RNNs from a transformer, and then from music transformer that has the relative attention, and kind of let you hear the differences, and then I'll go into how we what are the modifications we needed to do on top of the transformer model. So here, this task is kind of the image completion task. So we give it an initial motif, and then we ask the model to do continuations. So this is the motif that we fed. How many people recognize the? Awesome, okay. Yeah, so this is a kind of a fragment from a Chopin etude piece, and we're gonna ask the RNN to do a continuation. So you can hear, like in the beginning, it was trying to repeat it, but very fast it wandered off into its other different ideas. So that's one challenge, because it's not able to directly look back to what happened in the past, and can just look at kind of a blurry version, and that blurry version becomes more and more blurry. So this is what the transformer does. A detail is these models are trained on half the length that you're hearing. So we're kind of asking the model to generalize beyond the length that it's trained on. And you can see for this transformer, it deteriorates beyond that. But it can hold the motif pretty consistent. Okay, you get the idea. So initially, it was able to do this repetition really well. So it was able to copy very well. But beyond the length it was trained on, it kind of didn't know how to cope with like longer contexts. And what you see, the last one is from the music transformer that thinks about kind of the relational information. And you can just see visually how it's very consistent in kind of repeating these larger arcs. Yeah, so that was music transformer. And so in music, the self-similarity that we talked about, so we see the motif here. So there we primed the model with a motif, and this is actually a sample, unconditioned sample from the model. So nothing, there was no priming, but the model kind of had to create its own motif and then do continuations from there. And here, if we kind of look at it and analyze it a bit, you see a lot of repetition with gaps in between. And if you look at the self-attention structure, we actually do see the model looking at the relevant parts, even if it was not immediately preceding it. So here, what I colored, shaded out, is where the motif occurs. And you can see the different colors is the different attention heads, and they're kind of focusing among those grayed out sections. So I'll play you the sample, and we also have a visualization that kind of shows you, as the music is being played, what notes it was attending to as it was predicting that note. And this was generated from scratch. And so the self-attention is from kind of note to note level or event to event level. So it's quite low level. So when you look at it, it's a little bit overwhelming. It has like multiple heads and a lot of things moving. But there's kind of these structural moments where you would kind of see more of this clean kind of sections where it's attending to. Okay, so how did we do that? So starting from kind of the regular attention mechanism, we know it's a weighted average of the past history. And the nice thing is, however far it is, we have direct access to it. So if we know there are kind of motifs that occurred in the early on in the piece, we're still able to, based on the fact that things are similar, to be able to retrieve those. But it also becomes, all the past becomes kind of a bag of words. Like there's no structure of which came before or after. So there's the positional sinusoids that Ashish talked about that basically indexes into sinusoids that are moving at different speeds. And so close by positions would have a very similar kind of cross section into those multiple sinusoids. In contrast, for convolutions, you kind of have this fixed filter that's moving around that captures the relative distance, like 1 before, 2 before. And these are kind of, in some ways, like a rigid structure that allows you to be kind of bring in the distance information very explicitly. You can imagine relative attention with the multiple heads at play to be some combination of these. So on one hand, you can access the history very directly. On the other hand, you also know how you relate to this history, capturing, for example, like translational invariance. And we, for example, we think one of the reasons why in the beginning priming samples that you heard that the music transformer was able to generate beyond the length it was trained on in a very coherent way is that it's able to kind of rely on this translational invariance to carry the relational information forward. So if we take a closer look at how this works is the regular transformer, you compare all the queries and keys, so you get kind of this square matrix. You can think of it as like a self-similarity matrix, so it's a square. What relative attention does is to add an additional term that thinks about whenever you're comparing two things, how far are you apart? And also based on the content, do I care about things that are 2 steps away or 3 steps away, or I maybe care about things that are recurring at kind of a periodical distance? And with that information gathered, that influences the similarity between positions. And in particular, this extra term is based on the distance. So you want to gather the embeddings that's relevant to the query key distances on the logits. So in translation, this has shown a lot of improvement in, for example, English to German translation. But in translation, the sequences are usually quite short. It's only a sentence-to-sentence translation, for example, maybe 50 words or 100 words. But the music samples that you've heard are in the range of 2,000 time steps. So it's like 2,000 tokens need to be able to fit in memory. So this was a problem because the original formulation relied on building this 3D tensor that's very large in memory. And why this is the case, it's because for every pair, you look up so you can compute what the relative distance is, and then you look up an embedding that corresponds to that distance. So for like this length by length, like L by L matrix, you need like to collect embeddings for each of the positions, and that's depth D. So that gives us the 3D. What we realize is you can actually just directly multiply the queries and the embedding distances, and they come out kind of in a different order because now you have the queries ordered by relative distance, but you need the queries ordered by keys, which is kind of an absolute by absolute configuration. So what we could do is just do a series of skewing to put it into the right configuration. And this is, just a quick contrast to show the difference in memory requirements. So a lot of times the challenge is in being able to scale, being able to be more memory efficient so that you can model longer sequences. So with that, this is, I can play you one more sample if we have time, but if we don't have time, we can go ahead. Okay, so this this is maybe about a 1 minute sample, and I hope you like it. Thanks. Thank you for listening.
Reading or something. Thanks, Anna. Great. So just sort of so relative attention has been a powerful mechanism for a very powerful mechanism for music. It's also helped in machine translation. One really interesting consequence of relative attention in images is that like convolutions achieve translational equivariance. So if you have, let's say, you have this red dot, or this feature that you're computing at this red dot, it doesn't depend on where this image of the dog is in the image, in the larger image. It just doesn't depend on its absolute location. It's going to produce the same activation. So you have convolutions have this nice translational equivariance. Now with relative positions or relative attention, you get exactly the same effect, because you don't have any, once you just remove this notion of absolute position that you're injecting into the model, once you've removed that, then your attention computation, because it actually includes, I mean, Nikki and I and a couple others, and Anna, we were actually working on images, and it seems to actually show better results. This now satisfies this. It can achieve translation equivariance, which is a great property for images. So there's a lot of, it seems like this might be an interesting direction to pursue if you want to push self-attention in images for self-supervised learning. I guess on self-supervised learning, so the generative modeling work that I talked about before, in itself, just having probabilistic models of images is, I mean, I guess the best model of an image is I go to Google search and I pick up an image and I just give it to you. But I guess generative models of images are useful because if you want to do something like self-supervised learning, where you just pre-train a model on a lot of unlabeled data and then you transfer it. So hopefully this is going to help, and this is going to be a part of that machinery. Another interesting structure that relative attention allows you to model is kind of a graph. So imagine you had this similarity graph where these red edges are this notion of companies, and the blue edge is this notion of a fruit, and an apple takes these two forms. And you could just imagine relative attention just modeling this, just being able to model, or being able to yourself being able to impose these different notions of similarity between different elements. So if you have graph problems, then relative self-attention might be a good fit for you. There's also quite a position paper by Battaglia et al. From DeepMind that talks about relative attention and how it can be used within graphs. So while we're on graphs, I just wanted to, it perhaps might be interesting to connect some excellent work that was done on graphs called message passing neural networks, and it's quite funny. So if you look at the message passing function, what it's saying is we're actually just passing messages between pairs of nodes. So you can just think of self-attention as imposing a fully connect. It's like a complete bipartite graph, and you're passing messages between nodes. Now, message passing neural networks did exactly that. They were passing messages between nodes as well. And how are they different? Well, the only way mathematically they were only different in that message passing was forcing the messages to be between pairs of nodes, but just because of the softmax function where you get interaction between all the nodes, self-attention is like a message passing mechanism where the interactions are between all nodes. So they're not too far mathematically. And also the message passing paper introduces an interesting concept called multiple towers that are similar to multi-head attention that Noam invented. And it's like you run K copies of these message passing neural networks in parallel. So there's a lot of similarity between existing, this connects to work that existed before, but these connections sort of came in later. We have a graph library where we kind of connected both these strands, message passing, and we put it out in tensor to tensor. So to sort of summarize, the properties that self-attention's been able to help us model is this constant path length between any two positions, and it's been shown to be quite useful in sequence modeling. This advantage of having unbounded memory, not having to pack information in a sort of finite amount of in a fixed amount of space, where in our case our memory essentially grows with the sequence helps you computationally. It's trivial to parallelize. You can crunch a lot of data, which is useful if you have large data sets. We found that it can model self-similarity. It seems to be a very natural thing, a very natural phenomena if you're dealing with images or music. Also, relative attention allows you to gives you this added dimension of being able to model expressive timing in music, this translational equivariance. It extends very naturally to graphs. So this part, or everything that I talked so far, was about sort of parallel training. So there's a very active area of research now using these self-attention models for less autoregressive generation. So notice at generation time, notice that the decoder mask was causal. We couldn't look into the future. So when we're generating, we're still generating sequentially left to right on the target side. And why is generation hard? Well, because your outputs are multimodal. If you want to translate English to German, there's multiple ways, and your second word that you're translating will depend on the first word. For example, if the first word that you predict was danke, then that's going to change the second word that you predict. And if you just predicted them independently, then you can imagine you can just have all sorts of permutations of these, which will be incorrect. And the way we actually break modes or we make decisions is just sequential generation. Once we commit to a word, that makes a decision, and then that nails down what's the next word that you're going to predict. So there's been some work on it's an active research area, and you can kind of categorize some of these papers like the non-autoregressive transformer, the third paper, fast decoding, the fourth paper towards a better understanding of vector quantized autoencoders into this group where they're actually doing the decision making in a latent space that's being it's either being learned using word alignment, fertilities, or it's being learned using autoencoders. So you do the decision making in latent space, and then once you've made the decisions in latent space, you assume that all your outputs are actually conditionally independent, given that you've made these decisions. So that's how they actually speed up. There's also there's another paper. The second one is a paper that does iterative refinement. There's also a blockwise parallel decoding paper by Mitchell Stern, Noam Shazier, and Jakob Eskreuth, where they essentially just run multiple models and rescore using a more they decode using a faster model and score using the more expensive model. So that's how it speeds it up. Transfer learning has had the self-attention has been beneficial in transfer learning. GPT from OpenAI and BERT are two classic examples. There's been some work on actually scaling this up, like add a factor as a efficient optimizer. There's a recent paper by Rohan Anil and Yoram Singer. There's also Mesh TensorFlow, which actually they've been able to train models which are several orders of magnitude larger than the original models have been trained. So when you're working in this large data regime, you probably want to memorize a lot of things inside your parameters. You just train a larger model. Mesh TensorFlow can let you do that. There's been a lot of interesting work. Universal transformers, sort of recurrent neural networks can actually count very nicely. So if you these cute papers by Schmidt-Huber, where you actually show that recurrent neural, the cell mechanism just learns a nice counter. Like if you can learn kind of A to the N, B to the N with LSTMs. So then universal transformers brings back recurrence in depth inside the transformer. There's a really cool Wikipedia paper simultaneously with the image transformer paper that also uses local attention. Transformer XL is this paper that sort of combines recurrence with self-attention. So they do self-attention in chunks, but they sort of summarize history by using recurrence. It's kind of cute. It's been used in speech, but I don't know if there's been some really big success stories of self-attention in speech. Again, similar issues where you have very large positions to do self-attention over. So yeah, self-supervision is if it works, it would be very beneficial. We wouldn't need large labeled data sets. Understanding transfer is becoming becoming a reality in NLP with BERT and some of these other models. So understanding what's actually happening is an interesting area of ongoing research for me and a few of my collaborators. And multitask learning and surmounting this quadratic problem with self-attention is an interesting area of research that I'd like to pursue. Thank you.
All right, thank you so much for watching. Tomorrow we'll do another lecture, which is natural language generation. I think Abby is going to take this lecture. But until then, thank you so much for watching. See you guys tomorrow.